All right, guys, welcome back. And so how do you get now to the lab manuals? It's always a question students asking me all the time. And so what I'm gonna do right now is I'm gonna show you how to get access to the lab procedures. And so the way you do it is by going to www.kbcc.cuny.edu. And so when you do so, you're gonna get to our college website. And so from there, you're gonna go to academics. You're gonna choose the departments. You're gonna click on it, and then you're gonna scroll down. You're gonna find the Department of Physical Sciences. And so you're gonna click go, and then on the left-hand side, you're gonna see here a link to the laboratory manuals. You're gonna click on it, and then you're gonna scroll down, and that's where you're gonna have all different manuals for different courses in here. And of course, now we are talking about now here Science 25, and here you're gonna scroll down, you're gonna see all of the manuals here for Science 25 course. So I'm gonna click now on this manual, and here we have now the PDF file now of this experiment. And so the first experiment number 1, will be the metric system density and temperature. And so what I wanna do now, guys, I'm gonna take it here, and I wanna go over now the rules of significant figures, or guidelines is also the term to use here. The reason is, why do you need to know the rules of significant figures? And the reason is very simple, is that you want to know the certainty and the uncertainty in the measured value, or the measured number. And so now the rules now of the significant figures will tell you now how many digits are significant. And what are the significant digits? When you take a measurement, the significant figures are all digits that are certain plus 1 uncertain. And that's how you know the total number of significant figures. But there are also, of course, rules that now go to the very specifics of the different numbers and letting you know which number has so many significant figures and which number has other number of significant figures. So let's start with the rule number 1. And the rule number 1 here is telling us that non-zero digits and the 0 digits that are between the non-zero digits are always significant. Now, I'll give you guys an example of non-zero digits here, 434. All of these digits are always significant. And so here you have in this number 3 significant digits. Now, I now captured the 0 digit between non-zero digits here, and of course, according to this rule here now, the 0 digit is always also significant. And so now when you read, take a look at this number, and you start counting the significant digits now here, it's gonna be also 3. And I can give you guys an example of any other numbers. Again, as long as you got non-zero digits, always significant, all of the numbers listed in that particular number. And or if you have now a 0 captured between the non-zero digits, that 0 is always significant. Just have to count 1, 2, 3, 4, 5, whatever the numbers are there. And those will be significant. Now, rule number 2, zeros to the right of the non-zero digit containing a decimal is always significant. And here I give you guys a couple of different scenarios here. Scenario number 1, you got now a dot, a decimal here, and you got the 0 that follow a non-zero digit. Just remember, these zeros that follow the 3 in here, always significant. And so you're gonna count, these don't worry about, they're not significant. It's gonna be covered now in the next rule. So you just count 1, 2, 3, and you're gonna count these 2 zeros significant. And so the total number of significant digits here will be always now 3. Next one, well, you may have something like this. You have a number, dot, and then the zeros will follow the dot, the decimal. Guess what? Anytime you have a dot and 1 and whatever the number above the 1, all of the digits will be always significant. So now in this case, you're gonna have 4 significant digits. Okay? And again, it's pretty simple. You just have to remember the rules, the guidelines, the rules, whatever you guys want to call them. Now the next one is number 3. Zeros to the left of the leftmost non-zero digit are not significant. And here, you know, a lot of times now students have troubles with this rule, but it's a really simple rule. All right, so how do we manage it now? So, well, let's see now, we now follow the rule. We got a 0 dot and the zero that are trailing after the dot. As long as this is zero and there's a dot, whatever the trailing zero, including this one, they're not significant. They're just the placeholder. Because what you can do now, you can express this number as in the scientific notation, and this number will be in the scientific notation will be 3.00, again 3.00, three significant figures, times 10 to the negative 1, 2, 3, 4, to the negative 4. So now this number can be expressed in scientific notation as 3.00, 10 to the negative 4. So not only that you can count straight from here, number of significant digits, 1, 2, 3, you got 3 fixed in here. But you can also express this number now in scientific notation as 3.00, 10 to the negative 4, and now you see vividly that that number has 3 significant figures, that's 3.00. Okay, another case could be that, for example, this one, 0.05. Again, look, this number here before the dot is 0. Right away, whatever the trailing zeros before they hit the non-zero digit is always not significant. And so in this case now, you only have 1 significant digit. And so you can also express this number in scientific notation is 5, 10 to the power of negative 2. Now, you see how it said 5 and not 5.0. But if it were a 0 in here, followed the 5, then I would have said 5.0 because now I would have followed this rule here because I would have had now 2 significant digits. But here only, the way it's stated, 1 sig fig. Next rule. Number 4, also important. Zeros to the right of the rightmost non-zero digit may or may not be significant here. And I know the may or may not brings some ambiguity here, but here's how we resolve the ambiguity. As long as you got this number, for example, 5,000 here, and there's nothing else in here, no dots, no bars, nothing, guess what? You don't know whether these zeros are significant. And so you will assume that there's only 1 sig fig, which is a 5, because it's a non-zero digit. But once you see a dot in here, that means everything here is significant, all of these zeros. Anytime you see a bar over one of the zeros, that zero will be always significant. Anytime you see the bar over the 2 zeros, those zeros will be significant. Anytime you see the bar over all of the zeros, all of those zeros will be significant. Okay? Now, you could have also expressed this number as 5, and the scientific notation, 10 to the positive 3 power. And again, 5, 10 to the positive 3 power. That means you only have 1 significant figure, which is 5. Now, what about this case? How would we express now this number in terms of proper scientific notation? And so we would have said it now, these zeros are significant. 5.000, 10 to the positive 3. And so now you have in this number 4 significant figures here. Now, what about this number here? When you have bar over just 1 0, you would have expressed it as 5.0, 10 to the positive 3, 2 significant figures. This one now is 5.00, 10 to the positive 3 will be now 3 significant figures. So why are we doing this significant figure now business? Is because once we're going to start measurements, you will see how important to know the rules, because without the rules, you will have now the answers containing whatever the digits that you desire, but that's not the way we work in science. We're not working by desires, but we actually are working by scientific facts, and then we use the scientific facts to come up, draw certain scientific conclusions. Okay, now, a couple of more things I want to mention before we go into the measurements, before we go to the next, module of this experiment. All right, so now I decided, guys, to go back here, and now I got my marker and express these numbers here in the scientific notation. So this number here will be, as I mentioned before, 3.00, 10 to the 1, 2, 3, 4, negative 4. This number here will be, again, 3 significant figures. This will be 5, 10 to the negative 2, 1 significant digit. Here you will use 5 times 10 to the positive 3, 1 significant digit. This one is 5.0, 10 to the positive 3. This one here is, let me just take it out here, I have space, 5.000, 10 to the positive 3, and again, 4 significant figures, 4 significant figures. And this one is 5.00 here, 10 to the positive 3, okay? Now, what about now this number here? Actually, I took care of it here. Now this number is okay. You can also express the scientific notation, but that's, you can do it now. So the way, I know there is, you guys are supposed to learn it in your schools, how to do now the scientific notation of a number, transferring it or converting it from the standard notation. But let me just go over it real quick. So the way you do it using this model, n is equal 10 to the power plus or minus lowercase n. And so this n must be from 1 ranging to 9.9999 to infinity. And then this number here is the number of times you have to move the decimal here, left or right, depending on the number. So that you're gonna make now this number here between 1 and 9.999. So, to infinity. So, for example, in this case, I needed to make now this number from 1 to 9.999, and the way I did it is I moved the decimal 1, 2, 3, 4 times to make it a 3. That's what I did here. And so there you go, 4, number of times I moved the decimal. Okay? Number of times I move the decimal. Okay? And then what about plus or minus here? And the plus or minus, one of the rules they usually use is like the inverse relationship that you establish here. I think it makes it a little easier to determine plus or minus is by realizing that when you move the decimal and you increase this number, therefore you must decrease now the exponent. Because otherwise, if you don't do it, the two numbers will not be the same in terms of magnitude. Okay? So anytime I increase now this number, I will decrease now the exponent, meaning that I put a negative here to make it just simple, you know, for you to realize. And anytime, for example, in this case, I'm moving the decimal now, making this number smaller than the original number by 1,000. I'm going to make now this exponent positive here, because now this magnitude of this number will be equal over, you know, after all, the magnitude of the original number. Okay, again, if you're increasing the original number, make a negative exponent. If you're decreasing the original number, make the positive exponent. And that's how you, pretty much in a nutshell, convert the digit that is in the standard notation into scientific notation. Okay, so now we have a dilemma here that, let's say we did the measurement, which I will pretty soon do. You got several measurements, and these several measurements, let's say, we're done with a different equipment that has a different degree of accuracy and precision. So in other words, you have one instrument, one device that gives you 2 significant figures, let's say, and another device gives you 4 significant figures. So how do you deal? How do you now get the final answer that contains now the correct answer, correct number of significant figures? It actually has the correct certainty in the measurement, or uncertainty, I shall say, in the measurement, because remember, you just had the devices that were inferior one of the devices, and one of the devices were the more superior. So you have to understand that the device that you're going to have, the inferior device, will be affecting the final value of your calculation here. And so, in order to now have that taken care of in terms of the final answer, how do you express when you have a more inferior device, like in this case, you got a device that only has 2 significant figures, where the other device has 7 significant figures. How do you now, what's the final answer you should get now to take care of, you know, that this number does not have more certainty than it's supposed to have? Okay, and the way we do it when we add, subtract, or subtract, add, is that we follow what's called the precision rule. And the way you do it now, I'm going to explain to you in very simple terms here. The precision now here, we're going to measure in which place now for this particular number. And it looks like this is the 10th place, the 100th place, the 1000th place. This one looks like it's the 10,000th place. So this is a pretty, you know, precise number here. But when you now use a second number, the second number precision here is in the 10th place. So when you subtract now or add the 2 numbers, you have to understand that the final result will be now having now precision in the 10th place, or again lower the precision. You're gonna choose now the number, whatever numbers you got here, 5, 2 numbers, 3 numbers. You're gonna go for the number that has the least precision, and so the final answer must be rounded off, guys, to that particular place of the precision. So in this case, we got the 10,000th place precision. In this case, 10th place precision. So the final answer must contain now the 10th place precision, because this is the least precise of the 2 numbers. Okay? Now, so now, and again, what I just did, I did the addition subtraction, guys, in here. Well, actually, it's subtraction addition in this case. And again, what I did follow the rules of the precision, and then this was precise in the 10th place, 10th place, this one 10,000th place, and of course I went with the final answer that would contain now the least precision here. And it came from this particular number here, so it will be in the 10th place. Now, also what I did here, I did the rounding off, and the rounding off, guys, I'm going to cover now separately after I've covered now the multiplication division. So what happens now with multiplication division? Here, multiplication division, guys, the rule's a little different, okay, from the addition subtraction. Here we follow what's called the precision rule. Now here, when you multiply and divide, the final answer expressed the same number of significant figures I wrote here as in the original number that has the smallest number of significant figures that is participating in the mathematical operation. Okay, so you're looking at the quotient, you're looking at the product, and so you're choosing, in this case, for example, I got the same numbers here. Now this number has how many fixed? 7, right? 1, 2, 3, 4, 5, 6, 7. And of course I followed the 4 rules I just outlined here. This number has 2 significant figures, and so when I multiply now or divide, my final answer must be expressed, guys, 2 significant figures in this case. So I don't follow precision anymore rule, guys, in here. Now, again, in this case I divide, and when you do so, you're gonna get a 92, and again, I already rounded off these numbers. I probably should have stated the original numbers here, but you can do it, and then you will see, after you round them off, you're gonna get, guys, only the final answer is 2 significant figures in this case, and 2 sig figs in this case. Now, how do I round off? Now, there are 3 rules to round off the numbers. Now, the first rule now, let's say you have a number. All right, let me have now something like this, this number here that we already used before, 3, for example, 0, 3, 5. And let's say that I want to now drop all the numbers and leave the 10th place in here, the 3 in here, I want to leave. So I need to drop now these 3 numbers. So the way I do it now, I go to the number that I want to drop, this first number that I want to drop, and all the other ones, of course, but I look at the first number that I want to drop. And so I examine it and see if it's less than the 5. And if it's less than the 5, I just drop the numbers and leave the preceding number unchanged. That's it. That's it. Nothing else, nothing more. Now, so now rule number 2 now here. If the number now is greater than 5, then I need to drop. And again, let me just make up now a similar now number, but I'm going to change, instead of the 0, I'm going to put a 6 in here. And by the way, let me just round it off now, 101.3 here that I just, dropped the 0 here and all the other numbers. Now again, I want to drop now the numbers starting with the 100th place in here. So I see it's a 6. And according to this rule, guys, what I need to do now, I need to drop this number, all the other numbers that follow, right? But because it's above 5, I have to now increase the preceding number by the increment of 1. And that's pretty much it. 0.4. Now, rule number 3, I usually don't see covered in chemistry textbooks. In some they do, but most they don't. But it's an important rule here. Now, in certain situations, what you're going to run into, like this one, for example, let me get again the same number here. 101, let's say 3035. And as you can see, I got a 5 in here. Now, if the 5 is followed by 0 or nothing behind the 5, so what you need to do now, what's called an even-odd rule. What does it mean, even-odd rule? I didn't explain it here fully, but I want you to remember just the terminology here, even-odd rule. And so what you're gonna do now here, you wanna now drop the 5 and round off everything to the thousands place in here. And so you're gonna drop this number down. And as long as this number, if it's an odd number, you're gonna increase this number by the increment of 1. Okay, and so now if you wanna round off this number now, you're gonna have 101,304, according to this even odd rule. But what if it were here 101.3045? Okay, for example, 101.3045. And so if I'm gonna drop now this 5, and this is now an even number, I will drop the 5 and leave the 4 unchanged, or even number unchanged. So that's what it means now, the even odd rule. And the reason we use this rule, and again, usually it's not explained in the chemistry textbooks or physics textbook, is because it has to do with the statistical analysis. And I'm not going to go into statistical analysis to validate this because it's already been validated before me. Now, what if now you got a 5 and it is followed by a non-digit number? For example, we got this 101.3035, let's say 6. Okay, and I need to round it off this number here to the thousands place. So what's going to happen here now is that you're going to treat now this 5 as a rule number 2. Okay, so anything that now, if you want to drop now this 5, you will increase this preceding number by the increment of 1. And so you're going to have here 101.304. Okay, and that will be the final answer for this. If you want to drop again the 5, because the 5 follows now by some other digit, but not 0, you're going to follow the rule number 2, guys, in here, to treat it as if it was greater than 5. Okay, and that's in a nutshell, guys, the 3 rules how to do the rounding off. And again, if you have any questions, you know where to find me. You can always send me an email, and I can definitely go on Zoom and explain you now kind of face-to-face these rules with more examples. But at least from this discussion, you should be having some kind of a general idea on how to use these rules, how to round off the digits to the proper number of significant digits. And of course, through practice, through do more problems, I will reinforce your knowledge in this particular topic. All right, guys, I want to emphasize one more thing about the significant figures rules. And this one more point I want to make is that I put a note in here. And I want to emphasize the importance of this note in here, is that when you have exact numbers such as counting 1, 2, 3, 4, 5, something that has 100% certainty that you have 2 chairs, not 1.5 chair. You always have to understand that in those kind of situations, when you count, when you have exact numbers, you have infinite number of significant figures. Very important. Exact numbers have infinite number of significant figures. Now, the second point I want to make here about the significant figures is that when you have a conversion factor, which I'm going to talk about later on, that is within the same system of units contain infinite number of significant figures. Okay? Always. But if you have a different system now of measurements, such as, for example, SI system, or so when you measure length in centimeters, meters, and you try to now link it to the measurement that's being done in the English system, the only now exact measurement is 1 inch is 2.54 centimeters, and this should be treated as, again, two exact numbers, and don't worry about this being a limiting factor in during the calculation to determine the outcome, the final outcome, the final answer in terms of significant figures, because this is considered to be both of them, these numbers, in exact numbers. Now, any other measurements linking the system, for example, English system, and any other system, you will always have to understand that you don't have exact numbers there anymore, and you will have to consider now the number of significant digits in one system versus the other. So I will again go over this as I do the calculations, especially now I'm going to start making the measurements, And I will show you how now this will work when I do the measurement in one unit system, and I'm going to start converting that measurement into the other unit system. So let's go and start making the measurements. All right, and now we're at the point where we're ready to make the measurements now. And the way we do the measurements is that we report all of the certain digits plus 1 and certain digits. And these all certain digit plus 1 and certain digit is called now significant digits. And that's why I had to cover, guys, all of these rules, the guidelines for counting the significant figures, and how to do the calculation, mathematical calculation with the significant figures, multiplication, division, addition, subtraction, and also rounding off. So that when you get to this point now, when you need to start making the measurements and do the conversions, etc., you will definitely know now how many significant figures do I have with the measured number. When I multiply, divide, add, subtract, what is my final answer must be. So all of these that I just covered before will come here very handy, because otherwise you will have final answers that all over the place will have all kinds of digits, but not properly rounded off. So, how do I make a measurement? Well, it largely, of course, depends on the equipment that I have. Here I have these two rulers now, and I have this little block that I tried to measure with these two rulers here. And so you can see now this ruler here has more precision, where this ruler has less precision. Okay, now, so how do you take a measurement? Again, remember all certain digits plus 1 and certain. So I know certain digit here is definitely 2 because it is this measurement is between 2 and 3. It cannot be more than 3, it's between 2 and 3, therefore it must be a 2. So that's why I put here, it's a certain digit here. Now, the next one here, the empty space, guys, always must be estimated. And that's what I'm going to do next now. I'm going to estimate, let's say it's about 2.2, 2.3. It's, it's your call, really. So what I did, I just said 2.3, because this digit is uncertain and I had to estimate it, guys. Estimate it. So the last digit that is empty space between the numbers always has to be estimated. So now, when I look at this now, a measured value here, how many significant figures do I have? And then to answer the question, I have to go back to my significant figure guidelines. And remember, guys, the non-zero digits are always significant. So I have 2.3 means 2 significant figures will be now in this number. Now, next one. I now use the ruler that has now more precision. Now it's in the, looks like this one here is a tens place, but this one here is in the hundredth place. Okay, so how do I do the measurement now with this ruler? So the first thing, I know that I have to do the what? All certain digits plus 1 uncertain digit. And so my certain digit is definitely 2 because it's between 2 and 3. So I put it right there. And also what I can see, it's 1, 2, 3, it's between 3 and 4. So in the tens place, I know it's definitely 3 here. But when it comes down now to the empty space to estimate, remember, empty space always has to be estimated. This is where I'm going to be like, it's an estimated value. It's probably around 8, could be a 7, could be a 9. That's why this digit here is an uncertain digit, guys. And so therefore now, as you can see now, this particular ruler will give me only 2 significant figures, where this one will give me 3 significant figures. And this is how you know, to make the proper measurement here, okay? So now the next device here that I want to cover is called a graduated cylinder. So if you give you guys a moment what I'll do here, I'm going to bring one here to you. There it is. There it is. So how do I make a measurement now with this? And as I perform the density experiment, I will actually follow the rules here to determine the volume of the liquid in this particular device. Now, the way you do it is you always look, when you have the liquid inside of this graduated cylinder, at the bottom of the meniscus. Okay, it's very important. See, that's why I level my eye right at the bottom of the meniscus. So your eye must be at the same level, guys. So what I can see here now, but how do I know, what these individual increments are, how much volume they contain? And the way I do it is, there's a procedure, and this is what I'm going to teach you now, is that you take a look here, you take a look at numbers that are displayed on this graduated cylinder, in this case 15 and the 10, because I'm not interested about all other digits here, because my volume is between these two. And I'm going to do now 15 ml minus 10, and this procedure applicable to any graduated cylinders. 10 minus 15 minus 10, divided how many increments now in between? I counted 10, and therefore I put here 10 increments. And so when 5 ml divided by 10 ml, I got 0.5 ml in one or per one increment. And so now I know that the next will be a volume here, 10.5, 11, 11.5, 12, 12.5, 13. And now I know I definitely my certain volume here is definitely 13 because it's between 13 and 13.5. So that's why I got my 13 in here. Now what about how do I now estimate the empty space here? And it is a little conundrum here because you have to follow now a certain procedure. And the procedure I follow now, I can use this as a conversion factor, and I will teach you now the conversions in the next video in this particular lab experiment because you will be using a lot of conversions now, not only in this particular course, but if you want to become a health professional, you always have to know how to do conversions from one unit system to the other unit system, calculating the different dosage, etc., etc. So it's very important for you to gain those skills and be very good at it. So here's what I did, and I will explain to you guys later on the system here on how to convert from one unit system to another. It's usually you got given unit here is to cancel, desired unit on top, which will be ml, and I know I estimated it's kind of about 0.7 of the increment, 0.7 kind of fraction of the increment here, and I know that one increment contains 0.5 ml. I just determined it, and so this is also going to be looked as a ratio proportion, by the way. And I will again in the next video will teach you guys how to do these conversions. And so of course increment, same unit will cancel and the new unit will emerge, guys. So when you do 0.7, one significant figure, times 0.5, one significant figure. So remember guys, multiplication rule, you're choosing now, you're making the final answer to have the same number of significant figures as the the number that participating in this mathematical operation had the least number of significant figures, okay? So again, both of them have one significant figure. I got this answer, by the way, you see guys here 5 followed by nothing, but I need only one significant figure. Remember, this is now an odd number. I drop the 5 and I make it now from odd to even number, and that's why this is 0.4 here. You see how I just applied the rules that I taught you guys to everything that I've done in terms of calculation here. And so now, this number will be uncertain. Why? Because I estimated the empty space, guys, in here. And so remember the significant figures, all certain number, all certain digits plus one uncertain. So I got certain 13 ml plus one uncertain, and my final result here now of that particular volume will be 13.4 ml, and that will be your final reported measurement value. And you of course have here 3 significant figures, okay? And this is again, this procedure always guys work for any kind of graduated cylinders. And believe me, that could be confusing. But if you follow the steps, you're gonna be fine. And that's what I wanted you guys now here to cover in terms of how to do the measurements, how to count the number of significant figures, to what particular place you will express now your measurement, to what number of significant figures. So this was the point now of this introduction. I will also do now more concept covering here for the introduction. So I'll see you guys in the next video.